Let's talk about the difference between mass and weight. So, I have a GIF right here, and it's an astronaut that's kind of bouncing on the moon. So, this term bounce, right? When you think of astronauts kind of leaping across the moon's surface, they kind of bounce. So, why do astronauts bounce around when they're on the moon? Well, the reason for this is that their weight is less. But what is this term weight? Well, mass, remember, is the amount of matter an object has. So, like the amount of atoms in your body, what your body is actually made up of. So, for example, my mass is about 65 kilograms. Now, weight, on the other hand, is the force of gravity acting on an object. So it's how heavy I feel on the earth because of the amount of matter I have and because of the gravitational pull on my body, the acceleration of gravity, really. So weight is also called the force of gravity. Now, we know that force is equal to mass times acceleration, so therefore weight will be equal to an object's mass times the acceleration of gravity on whatever planet they're on. So if I'm going to find my weight on the Earth, the acceleration of gravity on the Earth is 9.8 meters per second squared. So what I do here is in order to find my weight, I'm going to multiply mass times the acceleration of gravity on Earth, which is 9.8 meters per second squared, and I get 637 newtons. Now, the key here is that mass doesn't change no matter where you go. So if I went to the moon, my mass would still be 65 kilograms. That is, of course, if I, ate a bunch of hamburgers and gained some mass, or I signed up for a marathon and I ran so much that I lost some of my mass, okay? Now, unless you gain or lose it, mass doesn't change if you go to the moon. However, weight can change depending on what planet you're on, which is why those astronauts look like they are lighter on the moon. It's because they weigh less on the moon. So if the acceleration of gravity on the moon is about 1.62 meters per second squared, what would be my weight there? Well, again, I know that weight is equal to the force of gravity. So the weight on the moon is the force of gravity on the moon. Now I know force of gravity is equal to mass times acceleration of gravity. And again, we're talking about the moon. So this is the acceleration of gravity on the moon. So plugging numbers in, I get that the force of gravity on the moon, or my weight on the moon, is equal to my mass, 65 kilograms, times the acceleration of gravity on the moon, which is 1.62 meters per second squared. And we end up getting that the force of gravity on the moon, my force of gravity on the moon, or my weight on the moon, is 105.3 newtons. Notice how much smaller this is than my weight on the Earth, which is why those astronauts look like they're bouncing around, right? The weight is less on the moon because the acceleration of gravity is less on the moon as well, which is why things actually fall slower on the moon because the acceleration of gravity is lower. Now let's do a couple examples with this whole term of weight now. So this cat right here has a mass of 5 kilograms. What is the cat's weight on the Earth? Now again, I know that weight is equal to the force of gravity, which is equal to mass times the acceleration of gravity. I also wrote equals m times g. A lot of the time we just write the acceleration of gravity as a little g like that. It's just a notation that we use in physics. So the force of gravity, or the cat's weight on the Earth, will be equal to its mass. I'm sorry, my dog is barking, probably because I'm talking about a cat. Its mass, which is 5 kilograms, times the acceleration of gravity on the Earth, which is 9.8 meters per second squared. So doing that math, we get that the force of gravity, or the weight of the cat on the Earth, is 49 newtons. Now, another example here, that what if there was an air resistance force of 10 newtons opposing that cat's fall? What would the cat's new acceleration be? Because we know since the cat is under the force of gravity, if there's no air resistance, it would accelerate to the ground at 9.8 meters per second squared. But if we have an air resistance force, that air resistance force is going to slow the cat down. So first and foremost, we need to draw what we call a free body diagram. Now, I'm going to go more into detail about free body diagrams next week, all right? But just know that we just want to label our forces, basically, on this cat. So number one, I know that the force of gravity that's pulling that cat down toward the earth, or the cat's weight, is going to be directed downward because the earth is attracting that cat. It's pulling the cat down. So that's the cat's force of gravity of 49 newtons. Now, the air resistance force is opposing the cat's fall. So since the cat is falling downward, air resistance is upward, and that's 10 newtons. Now, if we use Newton's second law to find the acceleration, I know that the net force is equal to mass times acceleration. In this case, I'm going to call down positive because I know that the cat is accelerating downward. Remember, it doesn't really matter what direction you call positive as long as you keep your signs consistent. So here, if I call positive downward, that means the force of gravity is positive, and then I'm going to subtract the force of air resistance because that's a negative force. So I have force of gravity minus the force of air resistance is equal to mass times acceleration. Plugging in my numbers, I'm going to get 49 newtons minus 10 newtons is equal to the mass, which is 5 kilograms, times acceleration. 49 minus 10 is 39, so I get 39 equals 5 kilograms times acceleration. We now, in order to solve for acceleration, I'm going to divide both sides by 5 kilograms, and I end up getting an acceleration of 7.8 meters per second squared. So notice how this acceleration is lower than the acceleration of gravity on the Earth because that air resistance force is slowing the cat down.